All right, welcome to another edition of IAEI News Live. My name is Thomas Dimitrovich, and today we're going to do, we're going to be in the home stretch of calculating fault currents on our little sample power distribution system, and it all starts now. All right, welcome back. Thank you for tuning in, and hopefully you're getting something out of this little series. I'll call it a mini series, where we are working on a small one line, and we're going through the per unit method of calculating available fault currents. We used complex variables. We modeled the system, created a impedance diagram, and now we're going to finish up. We're going to run through the calculation. I created a model in software, and I also have a spreadsheet. That's right, I also have a spreadsheet, and I'll pull that up as well. And that spreadsheet will be available to anybody who sends me an email. I'll give you an email address in a second here, or whenever we get to it. So that's our discussion today, and you might say, boy, this is a pretty math-intensive conversation, but you've got to understand, go back to basics. You know, as an engineer, if you're an engineer watching this, 4 years of, or however many years you went to for engineering, for an engineering degree, I think, in my opinion, any amount of schooling that you do get in your life teaches you how to learn. So this session is a walk back to the fundamentals, all the ways back to help you understand the power triangle, help you understand per unit, two very important tools, and then the practical application of it. And if you're going to sit for your professional engineering exam, you're going to need this information. So hopefully we're building a good foundation for those who are watching this and who care and are willing to learn and put some time into it. So this is a recorded session. I just want to say that really quick here. I should have started off this. This is a recorded session. I am traveling at this time, so I am out and about. And I wanted to make sure that I completed this and at least walk us through the next step, or set us up for the next step in our journey with this small power distribution system. But it is a recorded session, so and I might, if I can, monitor the chat. So please still chat it up, add your comments if you have questions. We will look at these in process. I do have a couple outstanding questions, which we will get to. We're not done with this one-line diagram. What I want to do after today's session, I want to get into selecting the overcurrent protective devices, because we have modeled the system. We've created an impedance diagram. We're going to model it in software application. I also have an Excel spreadsheet that we modeled it, and we have a hand calculation doing per unit calculations. So we will complete our discussion and select the overcurrent protective devices. We're not going to worry about selective coordination, and we're going to do an incident energy calculation, and then we're going to selectively coordinate this small power distribution system, and we're going to do our incident energy calculation. Then finally, we're going to compare our answers. So I hope you will stick with me throughout this process. All right, so where do we want to begin? Let's take a look at I did some homework for this one, so I made our little diagram a little better, I think. Anyway, so what did I do here? We have our utility. So now we're going to do the utility. We're going to model the utility, and I think if I'm not mistaken, I think I gave the X to R ratio, and I don't have it here. X to R is equal to 12. And you know what the X to R ratio is. What does that tell us? The X to R ratio, this is R, and this is X. And this is our power factor. If I know my X to R ratio, remember theta, which is my angle, is equal to the inverse tangent of X over R. So I can calculate my power factor for this system. And then I have a couple variables. I can eventually get to what my R and my X's are and everything else I need to know. So, but in any case, by giving an X to R ratio, that gives us the ratio of the inductive component to the resistive component of looking back at the utility. You'll notice I'm going to add a motor, and we're going to show you how you create your impedance diagram when you have a motor involved, and we'll calculate the fault currents. And I threw that into SKM Systems Analysis software, which you can use Easy Power, EDSA, and there's a few others out there that do the same job. So pick your preference, pick your tool, and then you can model these systems, and I'll show you a little bit about how I created and input the data into my software, and we're going to compare the numbers from a hand calculation. And you'll notice that I have a motor that has an X to R ratio, and I made it an X to R ratio of 5. Now, the information around impedances, we'll probably do just an hour session on all of the different impedances and where your sources of information can come from. From a utility perspective, X to R and your available fault current, that comes directly from the utility. They'll give you that information. Sometimes they may not give you the available short circuit. They might give you an MVA short circuit or some other values, which is perfectly fine. There are ways to work with that. I'm just using an available fault current from the utility. I put 80,000 amps. I have the X to R of 12. And this would be data that I would call the utility and have them send me that information for the specific location that I'm at. I'm assuming I own the transformer in this case, 4160 to 480, 5.75. Now, the large transformers, I could put an X to R ratio for that transformer as well. But we make a basic assumption that it's more X and it's all X and no R. Now that's it's a safe assumption, but if I wanted to break that 5.75% Z impedance into an X and an R, I could do that by contacting the manufacturer and finding information. I could also use IEEE rules of thumb in standards from standards documents to estimate what the X to R ratio would be. But I would, and I built a spreadsheet, and I'll have to open it up. It's on my computer, but we can play with some variables, and I'll show you why it really is not worth your time. So there are some aspects of impedance where you just make an assumption, either it's all X and forget about the R, because the R is so small it's insignificant. And we'll talk a little bit about that as we go down through this model. So I have, let's get rid of this. Try to keep it clean. I do need the X to R ratio. Get rid of that. All right, so we have a conductor C1, 6 400 kc mil copper steel conduit, raceway, 10 foot. We have a 2,000 amp panel board. I threw in 500 horsepower, which for our case, and what I probably could do, I could change that, but I won't. I mean, we once we get into the spreadsheet, I'll show you the impact of changing the size of that motor. We'll put it in and we'll take it out. And And you'll notice I didn't put a conductor. Whoop. I did not put a conductor. I didn't model a conductor to the motor. Why? Because I want the maximum available fault current. I'm not going to throw a conductor for this, for what we're doing. But if you did, I'll show you how the impedance diagram would be impacted. So now I have a motor, and we're going to show you how to do the impedance diagram. Coming off this, I have a conductor C2, 3/0 copper in steel conduit at 250 feet, going to a 500 kVA transformer, 3% impedance. I don't know what the heck. Yeah, delete that. 3% Z. And then I go to 350 kC mils copper, steel conduit, 10 foot, go into a panel board, a 1200 amp panel board. And you know what I'll do is I'll show you, once we get into the impedance diagram, I'll show you how we would model if we modeled a motor at that panel board as well. All right, so here's our impedance diagram. I have my, and I have to put my X to R of 12 here. I have to put my X to R is equal to 12. I have my utility at 80,000 amps, and I have to convert that to an impedance. I'll show you the equation that we use to get that done. I have my transformer T1 at 5.75%. I have my conductor C1, 400 kC mil. And each one of these blue squares is going to be an impedance. Now, you'll notice the 500 horsepower motor is an impedance, and you'll see where I have it connected, and I'll show you how you need to model it. But if I would have added, I'm going to make it red, if I would have added a conductor length to this motor, I would have added it right here. And there is a way. Where there is a will, there is a way. I think I go to style, and then I go to fill, and I go to red. There we go. I would have added a impedance in series with that. That would have been the impedance of the conductor. Okay, and I'll show you with this. So, and I did not model this, so I'm going to put Z conductor motor. So that would be the branch circuit going to that motor. Now, this is how we model the circuit. That motor is in parallel with everything up here. That motor is connected in parallel with back to the source. And if I would have put the impedance for the conductor, I would have done that. So it would have been the impedance going to the motor and the motor impedance in series with each other, all of that in parallel with everything from that panel board 1 back to the utility. If I put a motor down here on this panel board, I'm doing a what if, then I would have moved, I would have had a motor in parallel, motor 2, with everything. That's what the circuit would look like. And then I just simply have the process of basic circuits. Circuits 101 of how to add resistors in series and create equivalent impedances when they're in parallel. So remember what your basic equations are. In series, it's when you have two conductors like this, or two impedances, R1 and R2, the equivalent is R1 plus R2. They're just a series circuit. And when I have parallel, I would take, say I'm doing this, and this is R1, and this is R2. The equivalent, which is a single resistor, is R1 times R2 divided by R1 plus R2. That's basic circuits. How you add impedances in series and create equivalent impedances for circuits that are in parallel. So I look at this circuit and I just need to do the same thing. I need to, I'm not going to worry about the 50 horsepower. I'm going to take this out. Get rid of that. Actually, I'm going to get rid of that. And I'm going to get rid of this. I'm going to get it back to where we are. So what I would need to do is combine all of these in series and get a new Z. We'll call it Z new. And then I need to take Z new in parallel with that 500 horsepower motor equivalent impedance, which we'll calculate, to get what that circuit is, to get this to a single impedance so I need to add things in series first, combine them in parallel. That becomes the Z new here. And then I just add those impedances in series and I get my total impedance, and then I calculate fault current from that. And I'll show you how that's done. But that's standard network reduction. And you can imagine when you get a very large power distribution system, when you have many motors at all the different locations in the power distribution system, how many times you will have impedances in series and in parallel, and then you have to combine all of these, all of those, and then parallel with with one motor that's maybe connected way down below in the system. So the complexity grows the larger that your system is, but it's very doable, very doable. It just takes some number crunching and a lot of paper if you don't have the cool things like iPads. So now our job as power systems engineers is, the first step is to convert all of this information. I have to convert the utility with an X to R is equal to 12 into a Z at an angle. I have to create the transformer. I got to get that to a Z at an angle. And we did most of this. We didn't do the utility. We did the transformer. We did conductor 1. We did conductor 2. So all of that has already been done in the previous video. What's new this video is the utility and also the horsepower motor. And I will be showing you what I've done in the software, the SKM software, and we're going to compare our numbers. So I want to focus on the utility today and the motor. But this is the equivalent circuit, and I'll show you how it's done. All right, so we already know the complex variables. We know the R squared plus X squared equals Z. The theta is inverse tangent of X over R. We know R is equal to Z cosine theta. X is equal to Z sine theta. So those are very important equations. We know our, we know our per unit calculations. I'll move you back. We'll move you back over this way. There we go. We know our per unit calculations, actual over base. We know we picked 1500 as our KVA base. And we walked through, on the 480 volt side, we calculated our base current of 1804.2. We calculated our Z base of 0.1536, two very important numbers you're going to need. We also calculated the base values on the 208 volt system at 4163.6 amps is your base amps and 0.0288 as your base ohms. all of it on 1500 kVA base, 1500 kVA base. So we did all of that last video. Now, the per unit impedance, I need to convert that 50,000 amps. What did I say up here? I had 80,000. Well, let's do it with 50. We're going to do 50,000 amps, and we can do 80,000 as well. The basic equation is right here. You take the kVA base, which is 1500 kVA. You divide it by I short circuit, which is 50,000. Divide that by the square root of 3, and then you have the kV of the utility, which is 4160. So that's 4.16. This, and we can derive this, but I'm not going to go through the derivation of this. If you're interested in the derivation, I can generate that for you, but it's all based on the per unit values. Again, it's I base and Z base, V base, kVA base, all that jazz, all based, that's how we get the Z per unit. When you plug those values in, if I plug in 50,000, square root of 3, 4.16, 1500 kVA, I get 0.0042. And because we know the angle, we know the X to R ratio is 12. That means X over R is 12. Inverse tangent of 12 is 85.24 degrees. This is my impedance for looking back at the source. We call that the Thevenin equivalent. Good old Thevi, baby. Thevenin equivalent. That is if I was looking back to the utility from an impedance perspective, I would see 0.0042 per unit at an angle of 85.24 degrees. So that is my impedance for the source. Now, let's just say it was 80,000. Let's do it for 80,000. I have 1,500 divided by 80,000 divided by the square root of 3 divided by 4.16. Let me get my handy dandy calculator. So 1,500 divided by 80,000 divided by square root of 3 and divided by 4.16 is 0.0026. And it's the same angle, 85.24 degrees. So it went from 0.0042 to 0.0026. Now, what happens if I look at this equation? If I said the available fault current was infinite, I had an infinite amount of fault current available from the utility. What is my per unit impedance? I'm giving you why we call it an infinite bus. Because in this equation, my fault current is in the denominator. When I have an infinite amount, remember, Z per unit, any number, n, over infinity is equal to 0. So if I did 1,500 divided by 1, 2, 3 zeros, 4, 5, 6 zeros, 7, 8, 9 zeros, 10, 11, 12 zeros, 13, 14, 15 zeros, I get 1.5 to the times 10 to the negative 12th. The larger the number in the denominator, it approaches 0. The smaller the number, it approaches infinity. But when I say an infinite bus, I have an infinite amount of fault current available from the utility. My utility impedance goes to 0. And then what happens to my impedance diagram? What happens to my impedance diagram is, where's it at? Here it is. This goes to 0 and it just disappears. And I'm at the maximum amount of fault current because I have 0 impedance in for the utility. So when the utility's available fault current approaches infinity in the infinite bus, my impedance of the utility goes to 0. And it just eliminates it from the picture. That should tell you that that's going to give me the most fault current at any point in the power distribution system because my utility impedance is zip, 0. The moment I say 50,000 amps or 80,000 amps or 100,000 amps, let's do 100,000 amps. Let's do 100,000 amps. $1,500 divided by 100,000 times the square root of 3 times 4.16. Let's do the math. So 1,500, 100,000 amps divide 3 square root divide 4.16 divide 0.0021. Not much of a change from 80,000 amps. Let's do 200,000 amps. Now, what you should be seeing is the more current that I have, the higher the fault current, the lower the impedance. So 1,500 divided by 200,000 amps divided by the square root of 3 divided by 4.16 equals 1,500, 200,000, 3 square root divide, 4.16 divide, 0.0010. So my fault current is going up, my impedance is going down. An infinite amount of fault current gives me 0 impedance. Capiche? All right. Let's move on. This is transformer 1, which we already did. It's 0.0575. So it's equal to 0.0575 at an angle of 90 degrees. Because we're assuming it is all X. JX. This is 0.0575, and it's at 90 degrees. Conductor 1, we already went through this last. We have the R of 0.035 plus 0.049 ohms per 1,000 foot. We got to get it, multiply by 10 over 1,000 to get it to ohms per foot. And then I have to divide that by 6 because there are 6 conductors in parallel. That gets me to 0.001 ohms, not per foot, per 10 foot. And then I do my actual over my Z base, which we set up above was 0.1536. And there's my per unit ohms, 0.0007. We did the same thing for conductor 2, but we made a mistake 2 times before. We fixed that. There's now our transformer. We have to take the kVA base, the kVA, the percent impedance times the new kVA over the old kVA, and we get 0.09. That helps us account for that 3% is based upon a 500 kVA base, but we're at a 1500 kVA base, so we have to convert the 3% to the 1500 kVA. We covered that in our last week's session. Conductor 3 is the same as conductors 1 and 2. Same process to calculate my Z. And then we have all the numbers. Now the motor. Where's the motor? All right, so the motor. Let's go look at the motor. That's transformer All right, so let's do this. I did not do the motor calculation, but we're going to do it now. So I have 500 horsepower. Here's what I'm going to do. I am going to, how do I copy this? I'm going to do this. Copy. And we are going to create a page. Add page. And I'm going to do a paste. All right. I'll show you what I'm doing. So this is I have a 500 horsepower motor. Let's do this. I'm going to copy this. Copy. Paste. So I have this is actually, get rid of that. Let's move this down. This is motor M1, right? Motor M1. So we know we are at 16% subtransient reactance. 500 horsepower, we're going to assume it's 500 kVA. So we have 0.16 times 1500 divided by 500. Why? Because the 0.16 is based on a 500 horsepower. And I'm not going to do the 460. I'm going to say it's 480. So it's a 480 volt motor. We're not going to do the voltage. I'll do that, save that for another day. All right, so Z per unit is equal to 0.16 times 1500 over 500. So 0.16, 1500 times 500 divide is 0.48. 0.48. Inverse tangent of 5, because I said my 5 is equal to the x to r. My z per unit. So I take the number 5 and do an inverse tangent, 78.69 degrees. 0.48 at an angle of 78.69 degrees. We're doing good. So that is the per unit of the motor. Let's go and let's look at our impedance diagram. 78.69 to 0.48. Was it 0.48? Yeah, it's 0.48. All right, so I had already done the math, but I just did not do the math. All right, so this is motor 1, and it is in parallel with the utility, which is 0.0042, with the transformer 0.0575 at an angle of 90, with conductor 1, which is 0.007. Now, if you add let's just, well, I already did the addition. It's 0.0, if I add 0.0042 plus 0.0575 plus 0.0007, if I was going to do it manually, I would take 0.0042 times cosine of 85.24. Add that with 0 for the resistance of the transformer because it's at 90. I would add that with 0.0007 times the cosine of 54.46. And I would add that with 0.0623, or I'm sorry, I don't need to add that. So I would break this down into my R plus JX by taking R is Z times cosine theta, and X is Z times sine theta, right? So, and then I would add my R's and add my X's, and then do the R squared plus X squared square root and get 0.0623 at an angle of 89.3048. I threw more decimals because I'm trying to make it match these other programs that go out as far as they can to the right of the decimal. So I add all of that up and I get 0.0623, and then I take the 0.0623 times 0.48 at their angles, divide that. So I would, to get the Z equivalent, we'll call it Z equivalent, is equal to 0.0623 at an, Z equivalent is equal to 0.0623 at an angle of 89.3 times 0.48 at an angle of 78.69, and divide all of that by 0.0623 at an angle of 89.3 plus 0.48 at an angle of 78.69. So it's the product over the sum. And that is my equivalent impedance. So I'm going to do that with my calculator. So 0.0623 at an angle of 89.3048, multiply that by 0.48 at an angle of 78.69, multiply, and then I divide by the sum, 0.0623 at an angle of 89.3048 angle, and then I do 0.48 at an angle of 78.69. Add that, and then I divide those two. It's 0.055. So all of this can be replaced with one impedance, 0.0552 at an angle of 88.09. And how did I get 0.0552 at an angle of 88.09? I added the utility with this. I took that sum, multiplied it by that, and then it added that motor with the utility, transformer 1 and conductor 1 impedances, divided those two, and I get 0.0552 at 88.09. So that is that resistance value or impedance value. Then to get the full fault current, I take 0.0552 at an 88.09, add that with 0.0385 at an angle of 33.354, add that with 0.09 at an angle of 90, add that with 0.0052 at 52.04, and get the total. So there's our numbers. So let's do it. 0.0385 at an angle of 33.354. I'm adding that. 0.09 at an angle of 90. Add that. 0.0052 at an angle of 52.05. Add that. 0.1745 at an angle of 77.69. Let's do a 1 over that and multiply that by the base amps. The base amps. 0.0288. No, base amps, 4163.6. 4163.6 times is 23.9 kiloamps. 23.9 kiloamps. So I take, and what I just did was I did 1 over 0.1745 at an angle of 77.69, and I multiplied that by the base amps, which was, I know I'm going to get you dizzy, 4163.6, 4163.6, 4163.6, and that came out to be 23.9 kiloamps. All right, so, and that's with the motor in. Oh, I love this stuff. All right. So let's walk through the SKM. So here's my utility. I'm working without a mouse, so bear with me. So here's the utility. I'm going to double click on that. I have 50,000 amps, X to R of 12. I don't know if you can see that very well, but I'm trying. So I got 50,000 amps at an X to R ratio of 12. Here's my transformer, 1500 kVA, 4160 primary, 480 volt secondary. When you go to transformer impedance, this is your 5.75 is your percent X, and it's got 0.0058. It's effectively zero. There's my impedance of my transformer. Then I have a cable, which is, if you double click on the conductor, I've got 600 kc mil. Does that sound right? That says 600. Well, hold on. You know what? It doesn't really matter what it says, because you got to go to impedance, and I used 0.250, and you go to cable 1. Make sure I got the right numbers in here. Cable 1 is, conductor 1 is 0.035. 0.035, and X is 0.049. 0.049. All right. Let's do that. So that's cable 1. And then I'm gonna go to the motor. This is the motor. I got 480 volt motor, 500 kVA, because it's 500. You're making a basic assumption that 1 horsepower equals 1 kVA. And when you go to the ANSI contribution, there's my 0.16, and there's the X to R ratio of 5. And then we're going to come over to conductor number 2. I've got 4 conductors in parallel. That's conductor 1, conductor 2. 4 conductors in parallel. Let's go to impedance, 0.079, 0.052, right on there. All right. And then I'm going to scroll down. There's my transformer, my 500 kVA transformer. I've got 500 kVA. I've got 480 to 208. And the real important piece here is transformer impedance. I've got 3%. Let's do this, 3%, and I put a very high X to R ratio. So that's my 3%. And then I go to cable 3. I got 10 foot. So there's my 10 foot. I have 4 conductors in parallel. 4 conductors in parallel, and it should be 0.039 and 0.050. I go to impedance, 0.039, 0.050. Looking good. All right, and that should be it. I'm going to do a Control A and rerun the study. And now we're going to come down 23.8. And what did we get? We got 23.9. So that's pretty doggone good. And I would say the difference is rounding errors on all of my data. Now, let's do this. How much time we got? All right, got 45 minutes. All right, so we calculated. Now what I want to do is I want to bring up my spreadsheet. And I'm hoping I can get it on this. If I go to iCloud and I go to Documents, I go to IAEI, IAEI News Live, Presentations, and I go to Fault Current. There is my Excel spreadsheet. It's got to download it. Come on and work. Have to hit the little download button. Actually, I'm just going to call it up on here. So hopefully I can get this to work. Because what I want to do is I want to show you a couple items. All right, here we go. All right, nope, I don't have to do that. Okay. So here is my utility, my T1, C1, C2, T2, and C3. These are my impedances, my Z and my angle, my R and my X. So here's what we're going to do. This doesn't have the motor contribution. So without the motor contribution, I had 23.9 with 500 kVA of motor contribution. 23.9. Without motor contribution, it's 22.96. So about 23 kiloamps of fault current without the motor contribution of 500 kVA worth of motor. So we could, in fact, this is what we'll do. Let's do this. Let's go into SKM and let's change this motor. We're going to change the motor to 1,000 horsepower. That's 500. We'll just change it to 1,000. Control A, run. And let's take a look at what the fault current is. It's now 24,554. So 24,554. We went from without any motor contribution, 23 kiloamps, 22.96. So 23 kiloamps with no motor contribution. With 500 kVA of motor, 500 horsepower motor, we went to 23.9. And then with 1,000 horsepower motor, with the same impedance values, I went to 24.5. Now, more motors, more current, right? But I just wanted to show you the magnitude of how much motor contribution you get from the size of the motor, than the amount of kVA motor that you have connected, okay? So that's the first little piece of the pie. Now, what if, and what I did here was and in this spreadsheet, if you want this spreadsheet, just send me an email. My email address, Thomas A. Domitrovich @eaton.com. So ThomasA D as in David, OMITROV as in Victor, ICH at EATON.com. Thomas A. Dimitrovich at Eaton.com. There's no dots or periods or anything in the Thomas A. Dimitrovich. Send me an email. Just say, I want that spreadsheet. Short circuit, whatever. I'll know what you're talking about. So what I did down here in the bottom, I have C1, I have the resistance per 1,000 foot and the impedance per 1,000 foot. I calculate the Z per 1,000 foot and the angle. You know how to do that. It's R squared plus X squared, the square root of the sum. The angle is inverse tangent of X over R. So I have ohms per foot. And that should be divided by 1,000. So that's ohms per foot. I calculate the length, the number of feet. I take 10 times that number and of the ohms per foot, and I get 0.0006 0216 at 54.46, blah, blah, blah. If you have 6 of those conductors in parallel, you divide that number by 6, and you get the angle. My per unit base, because of where I'm at the 480 volt system, remember my base impedance is going to be different from the 208 volt system. I get 0.1536, and then you get a final per unit angle and a resistance and an impedance. Then those numbers are basically placed up here for C1 and then C2 and C3, all 3 of those conductors. Now, and it automatically calculates the available fault current, which is 22,960. Let's say, for example, that I change the utility fault current from 50,000 amps to 100,000 amps. I'm going to change this to 100,000 amps. Return. What did that do to my fault current? I went to 23,225. 23,225 from 22,960. Let's say I went from 50, remember it's 22,960, and I'm going to make this 200,000 amps. I go from 22,960 to 23,359. What does that tell you? That I can take my available fault current from the utility from 50,000 amps to 200,000 amps. And down further in my power distribution system, it really does not significantly impact the available fault current at those remote locations or even the higher locations. Why is that? Because of that main transformer in my power distribution system. That 5.75% impedance, changing my utility from 50,000 amps all the way up to 200,000 amps. At the fault current down there at that 1200 amp panel board, I got 2 transformers I'm going through. The utility impedance, what did we calculate it as? What was that number? Remember the utility impedance? The utility impedance was only 0.0026. What's the impedance of the main transformer? 0.0575. And then the other transformer was 0.09. The utility impedance at 200,000 amps was 0.001. It's very, very small. So varying the utility available fault current because of that big hunk of iron in that transformer doesn't impact the fault currents downstream as much as you would think, or as much as some people would lead you to believe. And my wife just says she's watching the worst Christmas movie ever. I don't know what it is, but I'm curious. So anyway, what we did this time was let's do this. Let's go back to our impedances, okay? Let's put this back to 50,000 amps. Okay, and now I'm at 22,960. Let's change the length of that 250 foot of conductor. Remember, 22,960. I'm going to write this here. 22,960. 22,960. Right? I'm going to change this 250 foot length of conductor. I'm going to make it 500 feet. I went down to 19,801 from 22,960 equals that minus that. A difference of 3,000 amps. This was 250, right? 250. Okay, so let's do this. 22,960. Let's take this I short circuit up to 200,000. Whoop. I can't have that little dash on the end. That's 20,000. I'm gonna add another zero. 200,000. 399 amps deficit. I went from 23,359 to 22,960. Now let's do this. Let's do the infinite bus. Now I have an infinite bus. So my utility is 0 impedance. 536. I went from 22,960 at 50,000 amps, an infinite amount of current available from the utility, and it only went up by 536 amps. Think about that. And this is why I get frustrated in some cases when an individual will say, you can't mark available fault current because when the utility changes their fault current, it changes every minute of the day. Well, yeah, about 500 amps worth if the utility went from an infinite amount to, let's say, 200,000 amps. From 50,000 amps to an infinite was 500 some amps. It's 300 and some amps, less than 400 amps. That's not much of a swing at all. And if you're picking your interrupting ratings within 399 amps, you got other problems, in my opinion. So that gives you a flavor for the impact of, put it back at 50,000, which we had our hand calculation. Well, we saw the numbers came out almost identical. This one doesn't include the motor contribution, but in any case, all you'd have to do is just do some other minor math, which we could do later. But in any case, 22,960 at 50,000 amps. The bigger impact that you have on fault current is changing conductor lengths and transformer sizes. So if I change that transformer from 0.0575 to 0.03, I just went up by almost 4,000 amps. So much more of an impact changing out the transformer impedances than the utility swing of available fault current at the line side of that primary transformer. Let's do an undo. What else? All right. Okay, so we showed you the value of current in the power distribution system. We showed you how to model when you have a motor involved. We showed you how to calculate or represent the utility as an impedance in the power distribution system. We followed through with the impedance diagram, converting the one-line diagram to an impedance diagram. You understand the fundamentals of KVA. I'm sorry, of the power triangle and your complex variables. And we also understand per unit. We should. We have pretty much all the equations. So we calculated fault current. Now what we'll do, in our next session, we're going to pick our overcurrent protective devices. We'll calculate incident energy. And then we're going to selectively coordinate those overcurrent protective devices. And then we're going to recalculate incident energy. So hopefully you got something out of today's session. And I think if you want this spreadsheet, let me know. I will send it to you. It has all of the math functions in Excel. So at least you have an understanding for how you got to remember how the mechanics of Excel work. All right, so hopefully you are getting something out of these little sessions. If you're an engineer watching this, remember, you need to join IAEI, the valuable resource of networking and valuable information from the magazine perspective and other educational opportunities and networking opportunities. You hopefully will consider joining IAEI. Please let me know if you need help in that arena as well. We can help you navigate the waters and figure out how to get that subscription in. All right, so hopefully you are having a good day. Hopefully you're having a great day today. And thank you for joining in for another Tuesday of IAEI News Live. And again, I apologize for not being able to be actually live today. This had to be a recorded session, but we still got you the info. So hopefully you got something out of today's session. And thank you for what you do for the electrical industry. Thank you for what you do for electrical safety. And remember to stay safe and please, you know it, stay healthy. See you next week.